Waterloo, and we talked just about sketching for maximum matching.
Yes. Perfect. Yeah. Good. You can hear me, yes? All right, good. So I wanted to talk about some streaming lower bounds, but then I decided not to because I've been talking about those a couple of times recently, and then I feel like the audience will get too tired of that. So I'm going to instead talk about an adaptive sketching upper bound. Let me write a title. So 1 minus x bipartite. Can you see it or?
Can you use a darker pen?
Sure. This was just for the title. All right. This is better.
Yeah.
All right. Okay. Perfect. So I will go through what is this problem and I'll define it. One thing to say, this is an extremely simple algorithm. So there is no gotcha or like I'm not trying to hide anything. I'm trying to show you an algorithm which is like super simple, and I hope to just go through all of it in this stuff. All right, good. So what are we talking about? We are talking about maximum weight matching problem. The problem is just this thing. You have a graph. Great example. 1, 2, 6, 7, 8. So you have a graph. It's not necessarily even bipartite. You have some weights over the edges. And what you want to do is that you want to pick a bunch of edges that do not share a vertex, and you want to maximize the weight. Okay, so the standard maximum weight matching problem. And here, I guess the answer, for instance, will be 9. You can get a maximum matching of weight 9, and I don't think you can do better. And 9 is like you can pick this one and this edge. Sounds good? And yeah, let's say we can't do better. Cool. So this is a fundamental problem. Like there's lots of results known on this problem in different models. One nice thing about matching is that it's a very good problem to try out different algorithmic techniques for it. Like lots of, I mean, you've heard of complexity class P, no? And that has started when Edmonds started looking at non-bipartite matching and like designing classical algorithm for it. And so my goal is also doing that. We want to just develop some algorithmic technique in the context of matching. So we are looking at graph sketching. We talked about this model, I guess. So graph sketching is this. You're going to think of your graph as a very long vector of its edges, basically. You look at this n choose 2 pair of possible. So your graph has n vertices. You look at this n choose 2 pair of vertices, and this vector has, let's say for now it is unweighted. Okay, so you write 1 here, 0, 1, 0, 0, 1. This means that the first 2 vertices, for instance, have an edge between them. This is, instead of adjacency matrix, I just write it in a vector. Okay, so this is my graph. A sketching algorithm does the following. You pick a matrix A. You usually think of this. So this is a very tall vector. Think of multiplying it by a fat matrix of A of S times n choose 2. And when you do the multiplication, you get a smaller vector of dimension S. Okay. And these are, because this is integer, it matters the bit representation of A should be a small also. Otherwise, I can just multiply with one random matrix of very large values, and I just store everything in a single number. Okay. So one thing is that my matrix A also has a small numbers inside it. Like the representation of this S is just order S polylog n bits. Sounds good? Okay. So what?
Does A depend on n?
A, n, or G? So the question is that does A depends on n, on the number of vertices for sure, but should it depend on this graph or not? Okay, and the answer is no, but let me get to that. Okay, so if you do something like this, for sure this is not a lossless compression. Like you are going to lose something. This is n choose 2, you're compressing it down to something, so you are going to lose some information. But we would like to do this thing and preserve some certain property of the graph. Okay, I don't want to store the entire graph here. I want to do this thing, and then when I look at the sketch, I can find a large matching from it, or I can find a spanning tree from it. Does that make sense? Now, when I want to do that, the question is, how do I choose A? There is always an easy way. I can look at my graph, I find its maximum matching, and I just pick A in the way that pick those edges and put them here. Okay? That's not interesting. What you do in a sketching is that the matrix A is chosen without looking at the graph. You pick some distribution, like any other sketching. There's some distribution. You sample A from that distribution, and then you multiply it with this matrix, and then you get your sketch. Does that sound good? It's the same as sketching. I'm not saying anything new. And it's a very useful model. You can use it to design graph streaming algorithms. You can use it to create parallel algorithms, fast algorithms, etc. So we want to look at graph sketching in the context of the matching problem. Any question about the setting? So let me try to list, now that I'm using a board, it's hard to list lots of references, but let me just say something here. So graph sketching was introduced in this very nice work of Guha and McGregor. That they designed this model, and they show that actually you can solve lots of non-trivial problems with it. You can solve things like graph connectivity. You can find the edge connectivity and things like that. Okay. And then there are lots of work here. We now know, let me just list some results. We know how to find cut sparsifiers, or even spectral sparsifiers. Or we can do, let's say, delta coloring. This is and this is and lots of other things. So there are lots of problems. We can create a sketch for them. Oh, okay. We can create a sketch of size proportional to the answer itself, O tilde n. Okay. So one thing I forgot to mention here, that we want a sketches of size O tilde n. So I'm having a very large vector, and I want to compress it down to something which is proportional to number of vertices. And for most of these problems, it's very easy to argue that you cannot go below that. Okay. If you're outputting if you're outputting n edges in a matching, you cannot compress to something less than. Good. So there are lots of sketches of this one, and I can slightly distinguish between these. There are so these ones use really the real power of sketching. Okay. There are a bunch of other algorithms here also, for instance, for densest subgraph or for delta plus 1 coloring. They're more or less, you just do sampling. So you don't need a heavy machinery of sketching, let's say. You can just sample the edges and just use your sketches to do sampling. And then you can solve those problems as well. So, So this is a long list here. There are lots of problems we can solve. But if you notice, I didn't talk about matching. Okay, so for matching, for a while, we didn't know how to do graph sketching, in fact. And there is a good reason. You can prove that there are no efficient sketches for matching. So if my task is to get this graph, multiply it by some matrix, and get something that has O tilde n, and be able to recover a large matching from it. We know now that there are lower bounds that rule that out. So for matching, so it proves a very strong lower bound. It says that if you want to be able to preserve a large matching with a sketch of size O tilde n, the best approximation factor you get is only n to the 1/3. Okay. So you are not going to be able to get a good sketch for the maximum matching problem. Does this make sense? And there are some works here that we know exactly what is the complexity of this problem down to the constant, really, or like asymptotically. Okay. But I will not talk about that. Okay. This sketching these results tells me that we cannot solve the matching using the sketching problem, like this setting. Sounds good? So then what would you do? If this doesn't work, the next step, which was already looked at in this very first paper, is that what if I do adaptive way of sketching? So I cannot sketch it in one go, but maybe I can do this thing adaptively a couple of times. So what does that mean is the following. Remember, in the past, my sketching goal was that I design a distribution that has nothing to do with this graph. I sample A from it, multiply with my input, I get the sketch. Okay. Now, if I want to do this adaptively, I'm going to do this operations in rounds. In round 1, I do exactly the same thing. I sample A from some distribution D, and I'll get A times X. Okay. Let me call it A1. Sounds good? So I learned something about my graph. And now I'm going to design a distribution. If this was D1. I'm going to design a distribution D2 that this time D2 depends on my graph through this sketch. I learned something about the graph, so let me use that information. So now D2 is some function of D2 of A1x. Make sense? Maybe you look at the graph and you decided that these set of vertices are more important. I want to sample more edges from there. So my next distribution tries to sample more edges from there. I'll pick something from here. So now I'll sample A2 from here. I'll do the multiplication. I'll get A2 of x. So this is my second round. In my third round, I put these two together. This is the information I know about my graph. I design my distribution D3 and use that to sample A3. And I do this thing maybe for R rounds. So is the model clear? At the end, I just use this information to output, let's say, the match. Why is this useful? Well, the same way that you can use the sketches in a streaming setting, you can now use this to design a multi-pass streaming algorithm. If you need R rounds of adaptive sketching, you get an R-pass streaming algorithm. In the first pass, compute the first sketch, use it to do the sampling. In the next pass, use the next round, and so on and so forth. Okay. Or you get a multi-round parallel algorithm, a map-reduce algorithm. So the same thing. And here, again, this AGM paper, for instance, showed that if you do order log n rounds of this type of sketching, you can find something like minimum spanning tree, which we know you cannot do in a single round. So now let's do something simple. Let me see if there is anything to say. So I want to start with a switch to the more algorithmic part. So I want to show you a very simple algorithm that if you do order log n rounds of a sketching, allows you to recover maximal matching, which is a 2 approximation. So we couldn't get anything near that in 1 round, but in order log n rounds, I can get something. And by the way, the goal is to limit the number of rounds as small as possible. Log n is already large, but beyond, we don't really want to go even beyond that. The constant would have been ideal, but at least log n. Does anyone see actually how to do something like this? One thing I should tell you, sketching allows you to sample something from the graph. You can spend polylog n rows here and sample an edge uniformly at random from the graph. So sampling is like one of the simplest form of sketching. So in fact, all the sketching things that I'm going to tell you today fit into this set. They're really just sampling algorithm. I'm not going to use the power of sketching in any way. I just want to sample from it. And there's a simple way of getting a maximal matching. Just sample order n edges from your graph, okay, uniformly at random. So now you have order n edges. Compute a maximal matching over those edges. Okay. And then remove all the vertices that are matched. Now you have another smaller graph. Sample order n edges from that graph. Remove the vertices that are matched, and just continue doing this thing. And it's a greedy algorithm. You can just append whatever thing that you sample, you can just add it to the, like whatever matching you compute in each round, you can just add it to the end of the matching you have. So the algorithm is this. Sample. This is maximal matching and this is the entire algorithm. Sample order n edges, compute a maximal matching m of your sample, remove everything that you've matched, and recurse. And if you get M1, M2 that you're picking is disjoint from it. You remove the match vertices, so you can just add it to the end of it. And you get M3 and just add it at the end. And why does this algorithm work? Question?
Sorry, I was just trying to understand why you're able to do this only in log n rounds like this terminates.
Good. Yeah, so let's get to why this thing terminates. I will not prove this, but there are 2 ways of proving something like this. This idea goes back to Lubit's MIS algorithm. You can prove one of these 2. Both of these are true. One, number of edges in round R. You can prove that in each round, at least half of the edges of the graph are being removed. It cannot be that if you are sampling order n edges, if you start with a graph that has n square edges, after you do this operation and you remove the matched vertices, you cannot have too many edges left. And the intuition is that if you have too many edges left, that none of those edges should have been sampled. And if you have so many edges, why didn't you sample them? So one way is this, and a slightly more slick argument, you can actually say that the max degree is also less than n divided by 2 to the r. You can even prove something like this. The maximum degree of this graph keeps going down. And if you prove either of these things, you can prove that in order log n rounds, you're going to end up with, your graph becomes empty. You have a match. Sounds good? These are really easy exercises. You can prove them on your own in like 5 minutes.
Yeah, something about this recursion. I mean, you allow yourself O tilde n space, where n is the number of vertices in the original graph.
Yes.
But n keeps kind of decreasing, or something is decreasing as you go along. So one might expect you would do even better because in later rounds you would accelerate or something.
That's an amazing point, yes. And we don't know how to do it. For some other problem like maximal independence, that we can do it and we get order log n rounds. Here, for some reasons, it doesn't seem that works. That's a very good point. Yes. Any other question? So this is a general, this filtering or the like subsequent work called sample and prune. This is a very generic way of taking any greedy algorithm and implement it using these sketching techniques. Okay? You can implement many, many greedy algorithms for submodular maximization, for like finding base of like minimum weight base of a matroid, things like that. You can really implement it in this way. Okay? But 1 minus epsilon approximate matching is not, strictly speaking, a greedy solution. Okay, greedy just gives you 2. So we want to use something like this and go all the way to something that gives us 1 minus epsilon approximation.
I feel like should be lower instances where the speaking. Speaking of the previous question by Jelani, I feel like there should be instances where this peeling removes just a 1 over log n fraction of vertices per round.
That's
so
true.
Then basically for the first like log n rounds, the number of vertices doesn't really go down.
So yeah, so Michael's question is that this algorithm, like I think what Jelani was suggesting, you can interpret it that this algorithm itself should become better. Okay, this algorithm is tight. It's tight even in a stronger settings, that there are models of computation that you can define that, and you can prove unconditional communication complexity lower bounds in those models for algorithms in this family. Okay? So it's not entirely clear you can beat it. And you're completely right, peeling is not going to get better than log n rounds. But for the sketching problem itself, it is not known that whether you need log n rounds or not. All right, so let's do this. So let me say one other thing here before going to the algorithm. So this gives us two approximation. There are also some generic ways of boosting approximation of matching to something better. Okay, so some, let's say, boosting framework. They give you bounds like this. You can pick any algorithm that you have to approximate matching and repeat it adaptively a certain number of times to make its approximation better, reduce it all the way down to 1 minus epsilon. Okay? One good way of doing this thing, for instance, is to, like, for instance, Andrew had this paper in 5. You need 1 over epsilon to the power order 1 over epsilon repetition. So if you have an algorithm that can find maximal matching, if you adaptively run it, you figure out this is a in particular important part of the subgraph, you recurse on that part, you continue doing that. For unweighted, you can repeat it these many times and reduce the approximation to 1 minus epsilon. So you can now get something which is order log n times these many rounds of adaptivity and get 1 minus epsilon approximation. Let's focus on bipartite graphs for a bit, bipartite and size. On and Guha 11, I think, show that multiplicative weight, you can repeat it order 1 over epsilon cube very easily to reduce this thing down to 1 minus epsilon approximation. And with some more work, they showed, in fact, you can do 1 over epsilon square also. This, okay, let me just. So you can run something, you can use something like multiplicative weight update, run maximal matching, and get log n divided by epsilon square rounds of adaptivity and solve the match. And you can get this type of one using other things also. For instance, there's this auction algorithm that gives you that. That gives you the same type of thing. Sounds good? Okay. But this epsilon square seems a bit inherent to these approaches. Okay, to multiplicative weight, in generic form, there is always this thing. Auction algorithms, they do not let you go below this thing. Okay? And the question we want to ask is that, can I get even better dependence on epsilon or not? Can I, for instance, get log n over epsilon here? And that's the result here. Okay, so let's go first. So that there is order log n over epsilon down. So Anand Guha 18 showed that you can actually not necessarily repeat the maximal matching, but a slightly different algorithm. And in these many rounds of adaptivity, get 1 minus epsilon approximation to match. Okay, so you can go below this type of rounds. It's not a simple algorithm, really. This is a very complicated algorithm because it tries to do the following. It picks one of these approximation frameworks and want to say that, look, it uses log n over epsilon square iteration, but I want to do 1 over epsilon iteration of it in just 1 rounds of adaptive sketching. So you have to collect enough information from your graph to simulate many rounds of these frameworks. Okay? And it turns it into something very complicated. Then we had a result a bit more recently with Aaron, Yujiya, Aaron, and Kevin that gets this bound for bipartite and size. And the nice thing about that result was that it uses something entirely different than this framework. But the nice thing is that you really converge in that many rounds. You do not try to compress many rounds into a smaller number of rounds of adaptivity that makes it very messy. But still, this is not a simple algorithm. And what I want to talk to you today is a very simple algorithm that get that bound, log n over epsilon rounds of adaptivity, 1 minus epsilon approximation, works even for weighted non-bipartite matching. Okay. And the algorithm, yeah, I'll show you the algorithm.
What do you mean by bipartite?
Oh, bipartite and just not weight, just the cardinality.
Oh.
Okay. All right, so what is the algorithm now?
Separate, sorry, just same clarification question. So the AG18 work, so the AG18 work only showed it for bipartite graphs?
No, this also works in the general setting.
Okay, so the result that you're going to present is like the same, but different, like simpler
It's
algorithm.
Yeah, in terms of the result, it is just simpler. It doesn't give you a new bounds.
Okay, thanks.
In a sketching, in a streaming, it does something, but in a sketching, it doesn't give you anything. Good.
Thank you.
So let me just tell you the algorithm if there is no question. So the idea of the algorithm, I want to do the same thing, okay? But so I'm going to sample order n edges. But then in this step, instead of computing a maximal matching, you do something else. Let's say you compute a maximum matching. Okay. You have the power, the sketch is in front of you. So you compute its maximum matching. And then instead of just removing things, I'm not going to remove anything. I'm going to reweight my edges. I'm going to say that some edges are more important. Okay. And the way to do that is that you look at the edges that if you sample them, they would have given you a larger matching. And then you just increase their weight. Okay. So you sample a bunch of edges, you compute a maximum matching, and then you look at these edges that if I sample them, you get a better matching. Okay. So then you're just going to reinsert those edges back into your graph, okay, so that you sample them more. The question is, how do you interpret what are the edges that if you sample them, you get a larger matching? Okay. That's what we are going to do. So you sample, and to be specific, you sample order n over epsilon edges from the graph. Okay. let's think of G as being a multigraph, okay? So your original graph is a multigraph. So you sample these many edges from it. You compute a maximum matching. And just for now, let's say I'm again bipartite and cardinality. And I will tell you at the end how to extend the algorithm in one go to weighted and non-bipartite as well. For now, I'm talking about bipartite cardinality matching. Okay? You sample these many edges from the graph. You compute a maximum matching and a minimum vertex cover. Let's say U. Okay. Minimum vertex cover in bipartite graph is the same as matching. They're dual of each other. Okay? So you can compute both of them. So you now have those things. Then instead of doing removing, add so this is the entire algorithm. Okay. You look at the edges. So you sampled U. U is a vertex cover of H. You look at any edge of G that is not covered by U, and you place them back into the graph one more time. If you want to think of them as weight, you double their weights. So G had a bunch of edges. Okay. You sampled a small number of them, and you computed the vertex cover of that small edges. Then you looked at G. This is the vertex cover you created was on a sample. So it's not going to cover all the edges of the original graph. Some edges are not covered. Take those edges and put them one more time inside G. G is a multigraph now. Okay? Put them one more time. If you have seen Clarkson's low-dimensional LP algorithm, this is doing the same thing. Okay? These are constraints that are not satisfied. You just put them one more time. So next time you're sampling, you're going to sample those edges more. Okay, there are two copies of that edge. If you do uniform sampling, you're more likely to sample. Does this make sense? If it is easier, yes.
So when you add those edges, you add those edges with the corresponding weight, right? So
for a second, let's say you're right. If I was in the weighted
Yeah.
case, I will add them with the same weight.
Right.
But for now, let's say I'm in cardinality, so there are no weights. I just double their numbers.
I see. So you are not using the weight because it's a multi-graph now, right? So if you, okay, all right.
Yeah, the reason I didn't want to call them weights is because there are also weight on the edges.
Sure.
That is the weight of the problem.
Okay.
When you add like the edges back again, like is it just their probability, or like when next time you sample, you might sample like both edges?
You may even sample them twice. That's
Okay.
fine. Okay, but it will boost their probabilities. That is fine. John, how much time do I have?
You have about 10 more minutes. Just to be
Okay.
clear, you said maximum matching? Not
Yes,
maximum.
this is maximum, though. And this is important that it is maximum. All right, 10 minutes is enough to do this. So this is the algorithm. Let me do its analysis. It may help to think of this thing as you are defining weights over the edges. So you have a weight QE, originally equal 1. And if you do not cover it, you just double that weight. Not covered. Does it make sense? You originally, instead of repeating, this weight has nothing to do with the weights of the original graph. If you want, call them importances. Okay. Originally, every edge have the same importance. Edges that are not, are not like being covered, you double their importance. By the way, this means that you don't add them once. Like whatever things you had, you just copy the whole thing again back there. Good. So what is going on? The real important thing is that look at Q being summation E. The total the total weight of the edges that you have. Okay. This vertex cover that you are picking here does a lot more than just covering the sample. It almost covers the entire graph. Okay, in the following sense. What does this mean? It means that even though you picked U on a small sample, if you look back at the original graph, the total importance of edges not covered by this vertex cover is only epsilon times Q. Only epsilon fraction of the edges weighted by their importances are not being covered. Okay. This is somewhat analog of what we were saying about the degrees there. This has a one-line proof. Does anyone see it? Or?
The union bound.
That's true. But union bound over what? Yes, you can really union bound over all possible vertex covers and say that if you are not covering epsilon Q fraction of the weights, you are going to sample one of those edges through this process, and that vertex cover will not be even a valid vertex cover in H. If I get a chance, I'll prove this thing. It really has a one-line proof. Okay. But let me tell you why this finishes the argument if you just have that. Okay. So claim 1, U of R is less than. Let me be a bit more relaxed and put 2 here. If you do this process, this is going to do something very similar to multiplicative weight using Q as our objective, as your potential function. The total weights are going to increase very slowly. Okay. Why? Because only epsilon over 2Q edges are not covered. Those are the ones that you double their weights. Everything else, you keep their weights the same. So in one round, this is true that Q I plus 1 is less than Qi plus epsilon Qi. Why? Because these were the only part that you double the weight. There are very few things that are not covered, so you only double these weights. Okay? So you get this back. So Q is not increasing by much. Make sense? Yes?
So just notationally, sorry, notationally, Q to the power R is Q for round R, or it's Q to the exponentiated to the power R?
Sorry, you're right. I should do it maybe like this.
Okay,
round
cool.
R.
Thank you.
Yes. But this is an actual exponentiation. Right. This one. Yes. Good. Claim 2. So now how do I want to do this analysis? I want to do a primal-dual analysis. I want to say that, look, one of these things is going to happen. In each round, you are picking a vertex cover, no? What are sizes of these vertex covers? Suppose I did not succeed in solving the problem. These vertex covers are going to be a small, no? So let's say mu G is matching size. It's the maximum matching size in G. Okay. Suppose my algorithm is not doing something good, so it means that M is always less than 1 minus epsilon mu G. If M ever becomes large, I'm done. No, one of the matchings I found is a large matching, and at the end you just return the largest matching you found. That's what you do in the algorithm. Okay. So then M has always been a small. If M is always a small, what do I know? Now the only thing I have to use is Koenig's theorem. M is always equal to U. In a bipartite graph, maximum matching and minimum vertex cover are the same. Okay? So it means that U is always a small. Or in other words, these UIs that I'm finding across all the rounds, they are very small. Good? So it means that their average is a small. Okay? So define U star to be 1 over R summation I equal 1 to R UI. This is a fractional solution. Okay, you put mass over vertices. This thing is a small in total. But I want to say that U star cannot be a vertex cover of the graph. In fact, U star is going to be very far from a good vertex cover. Why? U star have size less than 1 minus epsilon mu g. Do I agree? It's a fractional vertex cover. If U star can cover all the edges completely, okay, then U star will become a vertex cover of my graph. A vertex cover that has size much smaller than the matching of the graph. The matching had size mu g. Okay. So U star itself cannot cover all the edges. In fact, maybe the subplane, there exists an E such that U star of U plus, maybe, let's say it this way. There exists an edge E such that E was not covered more than epsilon times R times. There is an edge in the graph that I did not cover it many, many times. Okay? Why not? Suppose every edge I cover them more than this, like, yes. Suppose every edge was covered more than 1 minus epsilon R times. When I take the average, it means that U star covers every edge at a ratio of 1 minus epsilon. So even if I boost its number and multiply U star by divided by 1 minus epsilon, that's a valid fractional vertex cover of my graph. And what is its size? Its size is less than mu g. Good. So there is an edge that I'm not covering. You know, this U star that I'm getting cannot be a 1 minus epsilon approximate vertex cover. Okay, if it is, then my graph has a vertex cover which is smaller than its matching, and that cannot happen. Does that make sense? If I have that, what does it mean? It means that there is an edge that has not been covered epsilon R times. Okay. So its weight should have gone very high. No? This is going to tell me that that one edge on its own contributes 2 to the epsilon R to the weight. Every time I didn't cover it, I double its weight. So its weight went very high. Good?
Why is it epsilon zero not 1 minus? Why is it not 1 minus?
This is the number of time it was covered. Okay, so then you were not covered epsilon R times. And each time that you are not covered, your weight gets doubled.
Oh, okay. I got it. So
Okay.
there is an edge that was not covered. Okay, I got it. Yeah. I got
Yes,
it.
was not
Yeah,
covered. Yes. If you put these two things together, it is going to force R to put these two together. It is going to force R to be less than log m over 4 log m over epsilon. This is just an inequality. You can bound this thing by 2 to the, I don't know, 3 epsilon R over 4 plus log m. I'm saying 1 plus x is less than to the 1.5x. That's just that. So if you do that, you can bound that you cannot run this for many times. And this part of the analysis is very similar to multiplicative. It is multiplicative, really. And you'll get this back. So after these many rounds, you're done, basically. Okay? One of your matchings should have been large enough. You can just return that. So, all right, well, I'm done. Good. So let me just take 1 minute to wrap up then. Good. So this was the algorithm for the bipartite case. For the non-bipartite weighted matching, the only thing you have to do is to change vertex cover to the dual of non-bipartite matching. That's the odd set cover. You are covering the edges by odd set size. I don't know what is the combinatorial name of it. This is just dual of matching polytope. Okay. You pick that. The rest is the same. And when you are doing the sampling, now that you have weights, you sample proportional to the weight of the edge as well. And the only thing in the bipartite case that, non-bipartite case that become a bit different is this argument. Because vertex cover, there are only 2 to the n vertex cover, but odd set covers, there are 2 to the 2 to the n of them. So you cannot just go ahead and directly union bound over them. But then you apply Cunningham-Marsh theorem from linear programming that you don't have to worry about all of them. You have to worry about a laminar family of them. Their numbers are small. Okay. The same analysis, like as it is, will go through for now. And that's all I wanted to say. Thank you.
Any additional questions for Sepehr?
You said it was in terms of, sorry. There was one comment you made that in terms of sketching, it was this. It gave you the same result as Angular 18, but in terms of streaming, it had applications.
So, for instance, in a streaming, this can be done deterministically. Okay, you don't need to do sampling. I can show you a deterministic way of finding the edges without any sampling. Okay? Which is very different when this AG18, you always have to do a sampling.
Oh, cool. Okay, thanks.
Any other questions? Okay, then, if not, let's thank him one more time. And we have a break for a little under half an hour. So 11:45 is the next talk.
Ladies and gentlemen.